welcome to the session. Greeting of the day. In the previous session, the last class, we have seen about the types of sensors. Types of sensors. On that, first we have taken a position sensor, a displacement, that is nothing but a potentiometer. One example, we have seen our potentiometer used to monitoring of the fan regulators, like that we have seen. In continuous with that, today we will see about the strain gauge, one type of sensors to measure the displacement of force applied or load applied and the change in length, maybe a compression or tensor, whatever it is. So before going there, we should know what is a strain. A strain element is a ratio of a change in length in the direction of applied load to the original length. From the original length, how much it is extended. Thus, we name it as strain of an element. Therefore, the strain changes of the resistance R of the element. We know each element, each object have its own resistance. Those resistance are known. From there, how much it is changed. The strain changes the resistance R of the element. Therefore, we can tell the change in resistance by the original resistance is called directly proportional to the strain value. This is the change in resistance by the original resistance, which is already we know. Therefore, we will get directly the value comes out is directly proportional to the strain. Right? So, we are preparing a strain gauge which looks like this. Each strain gauge belongs to a 4,000 rupees and it is one time usable. If the strain gauge exceeds the limit, then it breaks, then it is one time usable. So we have to maintain in between the limit. Then we are using the strain gauge. In this picture, the strain gauge has been pasted on a glass board. You can see this is the glass board, round glass board. Here the thickness, see, here the thickness is there. This dark region is the thickness of the plate. Right? We will go ahead. So the construction of a strain gauge, we know we are using for change in the displacement. So you see here, this strain gauge which contains a base width, which contains the base width, this one, and then the single copper nickel stitched as or framed as a wires in between this base width. See, this is the grid width. For our identification, we have a center marks and the gauge length, from here to here, from here to here. We understand the strain sensing part. This region is a strain sensing part. So the total base width and the base length. So how we are connecting this strain gauge has to be connected to the electrical wires here and here, here and here. So this two we have taken out. This two we have taken out and connected to the electrical circuits to gather the change in displacement in terms of electrical resistance. Okay? That is how it is made. See, these foils are made of. How these thin foils are made of a constant alloy of copper nickel combination. Copper nickel combination of 45 to 55 ratio. Alloy is made which is more conducting. It can be easily measured the change in displacement. Change in the tensile, change in the compression, how much it is. You will see a video also. Right? Right. So this is the general, the image, the same image, a focusing image. So see here the wire, a thin wires or one by one wires you can able to see here. It is connected here. Here you have to connect. Here you have to connect, take out the lead wires. Here it is somewhat compressed state, here foils. Right? A few images I have placed here for our understanding. In this image we have pasted this strain gauge in the plate, glass plate, in such a way to identify the displacement. In any object we can place. For the experiment we have placed it there. See, you can see the coil lines. Right. How it is? The resistance strain gauge follows the principle of change in resistance. That is what I am repeatedly telling. Change of resistance has been found. Has been found. The length we have pasted, connected to the electrical resistance. It breaks, or the object, the glass may be, or to our case for our experiment, the glass may be, a change in displacement is measured. Right? It comprises of pattern of resistive foil arranged as a shown in figure. So we have seen already this. These foils are made of copper nickel of 45 to 50% of alloy combinations. So these foils made of alloy, these foils are bonded to, we are working on any object, but this is bonded, these foils are already bonded on the plastic material like polyimide and or epoxy. Right? So you see, which I am telling here is nothing but this yellow board. This plastic material is nothing but this yellow board. The plastic copper nickel foil is bonded on this yellow plastic board. On this plastic board is pasted in this glass board. It means the object to which we want to measure the displacement. Right? This belongs to 4,000 rupees one time usable if it exceeds the limit. If it exceeds the limit. Right. This strain gauges are secured to, it means foil, the plastic board, and then we are securing over using the epoxy. Right? Secured to the workpiece using the epoxy. A paste we are using to connect this strain gauge with the glass board. As the workpiece undergoes a change in shape, due to the external loading, maybe a tensile, maybe a compression, maybe bending, whatever it is. According to the load applied, the change occurs. That change should be in limit. If the limit exceeds, it will show. The variant in electrical resistance we can see. We will see the video also. You will see. If it exceeds, it breaks. It should not. That small such variations also we are measuring through the strain gauges. It is a force measurement also. This resistance of strain gauge are the elemental changes, how it makes. So these changes in resistance can be dictated, which is proportional to the change in this electrical resistance. So displacement is proportional to the electrical resistance. Right here, I am playing a video of a strain gauge measurements.
This is Vijay from Dynatech in India. In this video, the procedure for getting a good strain gauge installation on glass beam is shown. The first step in strain gauge installation is degreasing. This is achieved by spraying CSM-3 degreaser on a gauze sponge and wiping the surface of the beam thoroughly to remove all traces of oily and greasy substances that are detrimental to gauge bonding. Next, the surface is abraded with a 600 grit abrasive paper to get a matte surface on the glass. A few drops of MPrep conditioner on the surface helps considerably, as it is acidic and detects the contaminants and removes them. Scrubbing is done with a cotton tipped applicator. Then a folded gauze pad is used to wipe away the liquid from the surface. One wipe in each direction starting from the middle. Wiping the surface in a back and forth movement will spread the dirt but not remove it. So wiping back and forth should be avoided. Final cleaning is done with neutralizer, an alkaline liquid that neutralizes the acidity on the surface caused by the conditioner. If the neutralizer tends to dry on the surface, more neutralizer should be used while scrubbing. Wiping away the neutralizer with a folded gauze pad, one wipe in each direction from the middle, will render the surface clean and ready for bonding a strain gauge. A glass plate is used as a working surface for handling strain gauges. The glass plate is cleaned with a few drops of neutralizer to ensure that it is free of dirt or dust. To handle a strain gauge safely, a blunt tipped tweezers such as the BTW-1 is used to remove the gauge from its packing and lay it on the glass plate which is cleaned with neutralizer, making sure that the top side of the gauge is facing up. To transfer the gauge to the beam, a special tape such as the PCT2M tape is used, as it does not leave its sticky mastic behind on surfaces. A length of 3 to 4 inches of PCT2M tape is laid over the gauge and its edge is folded to make a handle to lift the tape again. The tape is lifted from the glass plate at a shallow angle to minimize the bending of the gauge. It is positioned on the surface of the part, then one end is pressed down on the surface and the rest of the tape is pushed down gently. The gauge is inspected for correctness of the location. Then the tape is partially lifted off the surface at a shallow angle until the gauge is free. The tape is folded backwards to expose the bottom surface of the gauge. Next, a very small amount of M-Bond 200 catalyst is applied to the bottom of the gauge. The brush is swiped against the bottle top several times to remove almost all of the catalyst. Then the bottom of the gauge is brushed just once. All the solvent in the catalyst should evaporate, which normally takes about a minute. Then the tape holding the gauge is held at an obtuse angle to the surface of the part. A drop of M-Bond 200 adhesive is placed at the join of the tape and the part's surface. The tape is then held over the surface at a shallow angle and pressed down with a smooth sliding action using a folded gauze pad, pushing out all excess adhesive all the way to the end of the tape. Thumb pressure is applied over the gauge for at least 1 minute. About 2 minutes is allowed for the adhesive to set firmly. Then the tape is removed by peeling it back on itself along the surface. The gauge is examined visually for any apparent defects such as unevenness or bulging or inadequate spread of the adhesive or air bubbles under the gauge. The next step is to attach lead wires to the strain gauge. The gauge is covered with a piece of PDT-2 tape except for the tabs to protect the sensitive grid of the gauge during soldering. For single element strain gauges, a 3 lead wire connection is used to connect the gauge to an instrument as a quarter bridge. The conductors of one lead wire are separated from the other two, and the conductors are twisted tightly until the twist extends all the way to the insulation. The conductors are then tinned with 361A-20R solder, which has a lower melting point than most other solders. Fresh solder is applied to the tip of the soldering pencil to make a pool. The edge of the conductor is placed in the pool of solder, then fresh solder is fed into the pool as the lead wire is drawn away. This process is repeated for the other bundle of conductors. To have some flexibility between the conductors, they are separated at the insulation with a sharp knife. The conductors are then trimmed with a pair of diagonal cutters to have just over a millimeter of exposed wire beyond the insulation. The tabs of the strain gauge are also tinned with solder. The end of the solder wire is placed over the gauge tab, then touched with the tip of the soldering pencil, and a small amount of solder is fed into the tab before lifting the pencil away. The lead wires are positioned over the gauge tabs and held in place with a short length of PDT-2 tape. The lead wire is then heated with the tip of the soldering pencil, and a little fresh solder is fed into the joint before lifting the pencil away. This is repeated for the second lead wire. The solder joints are inspected for proper connection, and if necessary they can be retouched with fresh solder. The PDT-2 tapes over the gauge and the wires are removed with a generous application of M-line rosin solvent, brushing the area a few times to dislodge the tape, which can be easily lifted away. The tapes should not be removed with any force to avoid damaging the soldered connections or the gauge. The strain gauge and solder joints are washed with M-line rosin solvent to remove all traces of flux residue and blotted dry with a gauze pad. Cleaning with rosin solvent is repeated a couple of times to ensure complete removal of flux from the area. In all strain gauge installations, it is very desirable to have some flexibility in the lead wires to minimize the possibility of breaking of the solder joints due to differential movement between the beam and the wire during testing. This is done by clamping the lead wire near the solder joints, then pressing a small round object under the wire and pressing the wire down on the other side to create a strain relief loop in the wire. The lead wires are then anchored to the test part with Fa-2 aluminum foil tape, which has a strong adhesive backing. The strain gauge and lead wire joints are covered with a layer of M-Coat A protective coating, which is applied with a brush. The coating dries in about 10 minutes and the gauge is ready for testing. The gauge is connected to a model P3 strain indicator and the beam is loaded to see if gauge installation is satisfactory. An unchanging 0 after balancing the reading, stable and repeatable readings of strain under load, and a good return to 0 when unloaded indicates a reliable strain gauge installation. The extremely smooth surface of glass makes bonding of gauges to it a challenging exercise. The slight abrasion with 600 grit paper seems to have helped achieve a good bond.
Let's see here an image from the video. We have seen how to paste. From the video we have seen how to paste. It may be in this, when the tensor load is applied here, when the load is applied here, the strain gauge may be here to measure the displacement change. It may be on the circular object. Here we have the strain gauge here, we have fixed. Then we have fixed here for the bending operations. Any such cases can be made to measure the change in displacement. Right? You see, so we come to the applications where we can use this. See, in experimental stress analysis and failure analysis, if it breaks or it in limit, if it breaks, it's a failure. That we are analyzing through using this sensors, strain gauge element, right? And then in multi-axis stress fatigue testings, in fatigue testings and proof testing operations, everything should be in limit. That limit we are finding here. That change displacement we are measuring. The displacement should not exceed, then it is failure. So the residual stresses and vibration measurement, a small change, a vibration measurement also can be measured. We have seen from the video, the small having a weighting and measurement systems we have seen. The start measurements are bending. Right? That is what here the image shows. Here, this one. Okay, the bendings or the deflections of measurements, everything. It's nothing but a single word. You can tell it's a change that we are measuring. Maybe a bending, maybe deflection, maybe a tensile, maybe a compression, whatever it is. So that is what here also is pointing. Right? A compression or tensile or strain measurements can be done. The force measurements, a force measurement of hydraulic or pneumatic process, everything can be utilized. Impact sensors in aerospace vehicles and also in the safety precautions in the automotive industry. So such cases we have seen. So summary. From this session, we have talked about the types of sensors. On that we have seen the strain gauge. The explanations and the video we have seen elaborately the principle working, the applications and advantages. The remaining things we'll see you in the next class. Thank you.